Okay.
Okay. So, yeah, I have some vague plan here. We're studying these Gaussian designs in Grothendieck sense, or design, d'enfant, whatever. And these very Gaussian square-looking ones. And well, but actually, I'm ignoring the Gaussian aspect for a moment because, well, you know, I have some conjectures about how these Gaussian designs work, what the effective Galois group is. But I want to check these conjectures. God damn, look at that picture. There's a missing dot there. I miss a dot that hasn't been colored in blue. Sorry, that's gonna annoy the hell out of me. Sorry, I've completely ignored that cut. Yeah, so there's this whole Baez theorem. We're trying to understand that. We're particularly trying to understand it in the genus zero case because we've managed to be interested. We've managed to reduce the cases that we're interested in to the genus case for the moment. So basically, I'm trying to start out with a genus zero design and create from that a system, create from that in a nice conceptual way, reasonably nice, reasonably conceptual way, a system of equations where the solutions include fairly snugly the Baez functions, the Baez projections for that design. So, okay, so here goes. Sorry, that's the wrong thing to, pressing the wrong button here as usual. So, yeah, so, you know, we've played around this before. We've played around with this before, these Baez projections. And I think one of the buzzwords we had was Shabat polynomial. So there was a case where these Baez projections were, instead of the general genus zero case of rational functions, there was a special case where they were polynomials. And in that special case, I think the designs themselves were trees rather than graphs or something like that. And you know, I knew how to approach that problem of dealing with polynomials, dealing with a you know, an algebraic variety of polynomials, because, you know, I knew what the coefficients of I know what the coordinates of a point in polynomial space are. They're just the coefficients of the polynomial. But if I'm dealing with an algebraic variety of rational functions, then I didn't really know anything about that, about what the coordinates should be. Have you ever thought about this?
Thought about what exactly?
If you're going to have, like, if you're going to make an algebraic variety whose points are rational functions, you know, you're going to carve out an algebraic variety in the space of rational functions. Then, you know, to be an algebraic variety, well, to start out being in locally, you know, affine algebraic variety, you should have coordinate functions. You know, and like I say, the coordinates of a point in the space of polynomials, those are the coefficients of the polynomial. But what are the coordinates of a point in the space of rational functions? I had no idea how to approach that problem. You know, it seems like a big gap in my.
Is there anything worse than the? I mean, so you could use the coefficients of the polynomial on top and the one on bottom, and then there's like a scale ambiguity that if you rescale both by the same number, doesn't do anything. Is there anything?
Yeah, I guess that is a way to approach it. Somehow, I guess there's a way to approach that, but I just want to sort of beautify that a little bit. So there's some basic stuff here that I didn't know about, but that's kind of nice, I think. So what did you say? You're going to have the coefficients of the numerator and the coefficients of the denominator?
Yeah,
and then an annoying glitch of the scale ambiguity to deal with somehow. Yeah, so we're going to try to take that
like
approach.
one of those being monic or something like that. I don't know. There might be a better one.
Yeah, there's issues of monicness here. Yeah, these are maybe perhaps more glitches, or perhaps they're all the same glitch, so they'll cancel out or something like that. Yeah, we're going to try something like this, but it turns out to be nicer than I was expecting. So one of the things that's going on here is, okay, so you mentioned the numerator and the denominator. And, the numerator, that tells you a lot about the zeros of the rational function. And the denominator, that tells you a lot about the poles of the rational function. But unfortunately, in this design game, you don't just want to know about those two fibers. You particularly want to know about three very important fibers. So we need I invented this stupid word of, k-orator. So if k is 0, then it's the numerator. The k-orator is the numerator. If k is infinity, then the k-orator is the denominator. And if k is 1, for example, then the k-orator is the, what do we call it? I mean, it's just the polynomial. I'm heavy-handedly emphasizing the there. Maybe I should say the monic polynomial to try to normalize it something. The monic polynomial, whose zeros are the ones of, whose zeros are the fiber over 1 of our rational function. So, but more generally, right. I mean, more generally than so we have the one-orator, right? We have the numerator, the denominator, and the one-orator. And those are sort of all important in the design game. And we have to treat the one-orator on a footing, equal with the numerator and the denominator. So you kind of have to face this, that you need a fraction with 3 things instead of just 2 things.
Okay, so then you have more, looks like you have more gauge ambiguity to.
Yeah, but there's this triple transitivity of the whole game, points on the Riemann sphere. So
okay.
So somehow, well, maybe that wasn't really addressing your question, but that addresses some question. But yeah, so I thought I had to deal with this, and I do have to deal with this, but it turns out it's rather nice to deal with if I haven't screwed up too badly. Because what happens is that all the k-orators of a rational function, they're organized together very nicely as they're like a path. They're like an affine. If I didn't screw up, then they're an affine linear path, so to speak, in polynomial space. Like, I think the way, for example, if you want to get the one-orator from the numerator and the denominator, then I think I forget exactly what it is, but it's something like you subtract the numerator from the denominator or something like that. Let's just try to run through that calculation right now, okay? So let's say we've got this rational function f of x equals p of x over q of x. And we want this other polynomial. We want the one-orator polynomial. So so what's the basic property of the one-orator? Let me call it. Sorry. What letter should I use for the one-orator? P is for the numerator. Let's do that. Let's do.
All right.
Maybe I should change P to N for numerator and Q to D.
No, don't change it. I just crossed out huge amounts of stuff to.
Okay. But I just need a letter for the one-erator.
R.
R? Okay. I don't like that, but I guess we have to use it. So, okay, R of X equals 0. Sorry, let me not draw zeros in such a silly way. If and only if what? If f of x equals 1. So that's, how do we say that f of x is equal to 1? We say that
F of x minus 1 is 0.
Well, yeah, but we could just say p of x equals q of x.
Oh.
Right? If the
Yeah,
if the numerator and denominator are the same, then the fraction is 1. So so like I say, that suggests that we just have to subtract the numerator from the denominator, or vice versa or something to get the k-erator. Yeah.
I mean, you could have replaced 1 by k there and changed the equation a little bit if you wanted to. Sounds like you're heading in the direction of.
Sure. Yeah.
Doing all of them at once.
Yeah. That's right. So what are you saying? F of x equals k. Then
P of x is k, q of x.
Q of x times k.
Uh-huh.
Okay. And so what does that mean in terms of R of x? R of x is some affine linear combination. Is that correct? It's an affine linear combination of P of x and Q. I'm hoping it's an affine linear combination. So what is the expression here? So R of x equals.
Just subtract those.
That doesn't look affine linear, does it? What am I trying to say? P of x.
That does to me. Why, it looks linear.
Well, sorry, I'm getting confused here. So the monic polynomials, right? Again, there are two ways you can deal with this scaling ambiguity glitch, or there's probably multiple ways you can deal with it. But you can just kind of take the k-erator to be ambiguous up to a scale. Only define the k-erator up to it. Or try to normalize it to be monic, or maybe it works better if I normalize it to be co-monic, where the coefficient at the other end is equal to 1 or something like that. And I'm not quite sure what's the best way to do this, but I'm hoping that it will kind of work out about the same either way, so I can be careless about it. But of course, I might get myself into trouble by being careless like that. Let's see, I called this, so I'm sort of claiming that a rational function is sort of like an affine linear path in polynomial space. And I didn't completely clarify how that works, but that's this idea, the k-erator family is like an affine linear, I think, an affine linear path in the space of polynomials. And when I say path, I mean that it's parameterized by a one-dimensional thing here, this k. Let's see. So how would I normalize this thing? Okay, you said it already is monic. I thought, let's see, what am I trying to say? Yeah, shouldn't we what am I trying to say? Divide by something like 1 minus k or something like that. I mean, if P, right, if P and Q are monic, and I want to get R to also be monic. then I
That sounds
should-
right. Yep. Uh-huh. Yep.
I hope I'm saying this right. So first of all, when I say a path is, parameterized by a one-dimensional thing. But of course, mostly we're dealing with complex one-dimensional things here. So it's a little bit tendentious calling it a path because it's parameterized by complex one-dimensional thing. But my intuition is sort of helped if I call this a path in polynomial space. Thinking of a rational function as a path in polynomial space. The points along the path are the k-erators.
Very nice.
Say it again?
I know what you should say next is that it's really fun to think about the infinity orator.
Sure. Well, that's also known as the denominator.
Right. But anyway, letting k goes to infinity, you just get q of x. So it's defined, it has a nice limit.
Okay, that's good. I'm very glad it worked out that way because I've been being very sloppy about this. I had no idea it would work out that reasonably.
If you hadn't, if you hadn't divided by 1 minus k, then it would be nasty when k goes to infinity, but with that division there.
Yeah, and I've never actually tried to do this normalization before, so it's amazing that it actually seems to have worked out. But anyway, I mean, I think my previous way of approaching this was instead of having a one-dimensional family of monic k-erators, I had this two-dimensional family of unnormalized k-erators. And if the one-dimensional version doesn't work out correctly, then I would fall back on that two-dimensional version. But yeah. So so we're kind of saying that
but this one, sorry, I was thinking how great it was that this is nice even when k equals infinity, but it's terrible when k equals 1, which is one of the cases that one of the other cases where you're.
There's no way we can talk ourselves through it. I mean, what do you mean terrible? There's no limiting?
Well, you get dividing by 0 and the thing on top is not at all 0. So you're getting p of x divided by 0. Sorry, p minus q divided by 0. So
it should work out somehow, though. It should have some sensible meaning, or else maybe I haven't normalized things correctly or something like that.
There'd probably be some way to normalize it so that this blow up phenomenon would occur at a point that wasn't 0, 1, or infinity. And if you're mainly interested in those 3 points, you could.
Like I say, my fallback position is to use the whole two-dimensional family, of unnormalized k-erators. But
you mean you put any arbitrary numbers in front of p and q?
Yeah.
Behind. Yeah.
Yeah, but I was hoping there was a way to get away with just having a one-dimensional family by normalizing things the correct way. But we'll see how it goes. So these Bellier projections are typically going to be rational functions whose k-erator paths cross the discriminant in prescribed ways. So right, I mean, they should cross the discriminant. Right, there's this discriminant variety in polynomial space where polynomials have multiple roots. And so what am I trying to say? That k is a so-called critical value of the rational function. Precisely in case its k-iterator lies on the discriminant.
Lies. Sorry, I'm getting, what does that mean to say that that lies on the, what's the discriminant?
The discriminant variety is this variety in polynomial space. You know, where the
What do you have? Repeated
all those
roots?
polynomials that have, yeah, that have repeated roots, not
Right.
just a single root that's completely repeated, but among its roots, there's at least one pair that's repeated, and that's so.
When the k-iterator has repeated roots, what is that? Sorry, that's what you're talking about then?
Yeah.
What does that mean? That means that, sorry.
Yeah, that means that k is a critical value of this rational function. So, you know, there's critical points and there's critical values. You know, critical points are inputs, critical values are outputs. So, you know, am I saying this right? That critical points are where the derivative is 0, but critical outputs, critical values are, you know, outputs for which the fiber contains some critical point. And basically that means that that fiber is degenerate. You know, some point in the fiber has multiplicity greater than 1. So that means that there are repeated roots there. Hope I'm saying this more or less correctly.
Yeah, it sounds right. Yeah.
So yeah, I mean that there's a good reason here why we're interested in thinking of a rational function as a path, as this path of k-iterators in polynomial space, because that gives us direct access to thinking about the critical values, which is really important in you know, that's what Bétréma projections are all about. So what is it about? Definition of a Bétréma projection is sort of like that there are no more than 3 critical values, and you know, by the triple transitivity ambiguity that we can exploit, you can by convention think of those as infinity, 0, and 1, but if it's more convenient, you can think of them as anything else you want, infinity, 0, and k, or whatever. And so yeah, so a Bétréma projection is basically one of these rational functions which crosses the discriminant as an affine linear path in polynomial space. It's a path of k-iterators, that it crosses the discriminant no more than 3 times. I think that's a reasonable definition of a Bétréma projection. But in fact, right, in the larger game of Grothendieck-Teichmuller theory, seems reasonable to guess that we're going to be interested in things similar to this, but where we may cross the discriminant more times. You know, so if you, for example, if you cross the discriminant 4 times, then you might as well think of it as crossing at infinity and 0 and 1 and k. But you know, we kind of ran out of triple transitivity at that point. So now you actually have to think of as k as the actual, you know, cross ratio of these 4 points or something like that. And there's a moduli space there, a continuous moduli space, depending on the value of k. So I don't know, that presumably or guessably that's going to happen in the larger picture of Grothendieck-Teichmuller theory, getting beyond the case of just crossing the discriminant 3 times. But yeah, so okay, so let me go back up to here. And let me try to fill in that one missing blue dot. Where is it? Right there. Should I fill it in individually on all three of them?
Well, yeah, you did it. You duplicated before you corrected. I mean, you have to duplicate your correction or else destroy your duplications.
So, I mean, you remember that we created a, I mean, this is what, this is, if you just roll this up like into a torus, then this is a Gaussian design with 36 lozenges. No, is that 36 lozenges? It's 36 Voronoi cells. No, okay, it's 9 lozenges, 9 Voronoi cells. Those are the corresponding to the red dots.
Mm-hmm.
I always get confused about all these different. We've talked about how they're different choices. Yeah. So it's I think these smaller squares that we're seeing are the lozenges, if I didn't screw up. And so there's 36 lozenges.
Okay.
And
Mm-hmm.
yeah. So if you just wrap this up in the obvious way into a torus, then you can get this 36 lozenge design, a design with 36 lozenges.
Mm-hmm.
The lozenges are these, fundamental, what do they call those? Fundamental regions, fundamental
Domain.
somethings. Fundamental domains, okay. Actually, because of the non-homogeneity, I'm not sure we should call them fundamental domains, but they're little cells in these designs.
Mm-hmm.
But 36 of them, yes, but that's, but there are these more, that's a very regular design. But there are these more interesting irregular designs that you get by, so I mean, they're, right, we're sort of working over Z mod 3 here. Right, you can think of these red dots as like the affine plane over Z mod 3. And the projective line over Z mod 3 is these 4 lines through the origin that you, right? So there's like, right, where are they? It's like, there's that one, that one, that one, and that one. Those are the 4
Uh-huh.
points on the projective line over Z mod 3. So you can pick a point on this, right? You can wrap up further, by index. Let's see, what do we get? Here we have 36 lozenges. We're going to get it down to 12 lozenges. I guess. Yeah, we're right. So if we, let's think of this as the origin right here. Okay.
Yeah.
And so we can mod out by this point in the plane. Or we could mod out by this point in the plane. In other words, mod out by the translation by, translation by that amount. We're going to roll it up, mod out by that. Or we can mod out by this translation.
You mean mod out this torus we already have?
Yes. Yes.
Yeah. Uh-huh.
And both of these translations are order 3. So where we would be wrapping this up by a factor of 3. And that gives us, so you have this choice between doing it the horizontal way or the diagonal way.
Uh-huh.
And that gives us our 2 different designs that we suspect are in the same Grothendieck-Teichmuller orbit. So when you mod out by the horizontal translation, that gives you a very obvious thing, right? That just looks like, that's the thing that looks like this picture here, sort of just, you take.
Uh-huh.
But if you mod out by the diagonal translation instead, it looks more peculiar. And they're definitely not equivalent. But they're not strongly equivalent, but they may be equivalent under the Grothendieck-Teichmüller axiom. We're trying to settle that and understand that. And so yeah, let me.
So they're not isomorphic as elliptic curves, but over Q or something. But they may be in the same orbit of the Galois group on elliptic curves over Q.
Yes, something like that. Yes, this Grothendieck-Teichmüller group, or something like the Grothendieck-Teichmüller group, which is a kind of Galois group, maybe. I mean, I'm still trying to understand what it is, but what I'm really trying to do here, I'm just trying to get raw material that we can use for our K-iterator game here. So what am I trying to say here? That like, well, right, we're going to, right, I guess we should think of it as just taking this middle third. Let's take the middle third here, like there. Yeah, so that's a genus 1 thing. That's also an elliptic curve, but it's easier for us to deal with genus 0. So let's further mod this out by, mod out by 180-degree rotation. And that will be, we're modding this out by 180-degree rotation. And, so that it turns out that wraps this up into a genus 0 thing instead of a genus 1 thing. And that's sort of the usual way that, elliptic curves double cover the genus 0 Riemann sphere. So I'm just trying to get the combinatorics of the red and green and blue dots here to work correctly. So what am I trying to say? Let's try to figure out the green dots in here. So first of all, we started out with 36 lozenges here, but then we modded out by this order 3 translation. So that gets us down to 12 lozenges. That this 12 in the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. But then we're modding out by another 2 because we're modding out by 180-degree rotation. So like, this blue at the top is the same as this blue at the bottom because they're the same under the 180-degree rotation. So that gets us down to 6 lozenges.
Yep.
So that means that our numerator and denominator and our one-iterator are going to be 6th-degree polynomials. We're dealing with this path in the space of 6th-degree polynomials.
How do you know the number of lozenges is the degree of something?
Well, we thought about it before, and it made sense on those days. But let's see. What am I trying to say?
Oh, I guess because you've got like 6 roots, which are one of these color things, and 6 poles, which are some other color thing. Is that true that you get? Yeah, you have. I mean,
a rational function. A rational function. What am I trying to say? A rational function. Generically, a rational function that 6-fold covers. That is a 6-fold cover of the Riemann sphere by itself. Generically, that's got numeric. Numerator that's a 6th-degree polynomial and denominator that's a 6th-degree polynomial.
Yeah. Okay.
And if I could think more clearly, then I wouldn't just have to say generically. I could say it the right way or something like that. But generically, this is kind of what we're expecting.
It looks like you get 6 when you do this modding out by the 180-degree.
Yeah.
It looks like you get 6 green dots. Wait a minute.
You have to be careful. Yeah.
I don't even know if that's true. I was gonna say, like, it seems like you got fewer red things than you do green or blue. And I'm trying to figure out what that, I can't remember your conventions. What are the zeros?
Let me think. Let me think what you're saying. I'm hoping it's going to be red and green are going to be fewer, and blue is going to be more. That's what I'm hoping that's actually going to work out that we have the same number of reds and greens. Well, so first of all, it seems pretty easy to count the reds. It looks like we have, you know, before we did the 180-degree rotation thing, we had, you know, A and B and C.
Right.
But with the 180-degree rotation, we get it down to just A and B, and this is A right here.
Yep. So just move those.
You know, and if we wanted to, you know, label all the others, these would also be, am I doing this right? A, B, A, that's all A, B, A, etc. Okay.
I just want to see 6 of something.
I'll show you 6 of something in a moment. But first, let's count the
reds. Are going to be either 6 blue or a 6 green, or I mean, you said that there's like 6.
Yes, if we were looking at a sensible, normal, good fiber, then there would be 6.
Oh, okay.
So
these
but we're specifically looking at the bad, evil fibers.
Okay. So if I like look at the near the lower right-hand corner of a square, and of any square, I think of that as like some. Anyway, yeah, I get it. I mean,
but you have to remember that these things are rotating. So if
right, so it's even more confusing. But anyway, there's
right. But you could take the point that's very close to the green one, but not quite the green one, and then there are 6 of those. Yeah.
Okay. Yep. Okay. Fine. Right. Okay. So I believe you about the degree 6 stuff.
Yeah.
I mean, I believed you for a while, but I just wanted to
right. So yeah. Okay. So. Let me try to give a semi-conceptual argument that there should also be just 2 greens here. And it's basically because there's this, you know, duality between reds and greens here. Right? I mean, if you look at this whole tiling, you know, there's twice as many blues as there are reds and greens, but reds and greens are getting the same thing. They're just kind of, you know, diagonal. Like you can think of one of them as corresponding to the Gaussian integers, and the other one is corresponding to the d poles between the Gaussian integers. And those are the same lattice, basically. So I think of the reds as being I think of the reds as being the Gaussian integers, and I think of the greens as being the d poles. I mean, that's that's a very overblown word in this context, but the d poles between the, you know, so these are the corners of the greens are the corners of the Voronoi cells. Right. A Voronoi cell here looks something like that.
Yep.
And the corners are the.
Yep.
Did that undo it? I hope that undid. So okay, but now let's now let's try to actually label them and see that we really do just have 2. So what do we have? We have C. Yeah. Okay. Right. C. Yeah. It's C and C, and D and D, and D and D.
Yep. Right.
And now, what about the blues? So it's like E is up there, and E is down there, and what F is there, and F is there. And
so the midpoint of the verticals, yeah, that's F and that's F, and then right in next to the central B there are 2 more blue guys.
How does this work? Let's see. So
those have got to be Fs, because you notice that you got 2 Ds, one above the other by 2 steps. So there's got to be 2 Fs. There's got to be an F 2 notches above every other F.
Yes, but you just have to remember that, you know, sometimes above means upside down above. And we've already got that accounted for. Right, I mean, you know, this, right? These Fs are above this, above these Ds, I think, but these Fs are upside down above these Ds.
Yeah.
You just have to
Well,
get used to
anyway, are the
rotating.
two,
Yeah,
what are the names for the two blue dots to the left and right of that B? The central
left
B.
and right of the B. Okay, we call them G.
Those are the G.
Sorry.
Oh,
So
really?
first of all, okay,
They
let
really
me try to use let's see. So what did we do? We got up to C and D, right? And that was with green ink.
Yep. So now E and F are blue, and you're claiming that there are 3 blues, huh? I was thinking that
I'm hoping it's, unless I'm really screwed up, I'm hoping there are 4 blues.
Ooh, okay, wow.
So
Okay,
let's see if
well,
we can get 4 blues to materialize it. So we have E.
oh, I guess, well, I can, if I'm trying to get 4, I can do it.
That's what we're trying.
Well, I'm just trying it because you want me to. I can do a calculation to get any answer you want.
Let's see.
You're gonna claim that the guys left and right of that B are.
Yes, and I think it's right. So the only reason we had, no, I'm not saying it's right. That didn't work. Let's see.
But that's just 3,
F,
right? F, G. You wanna pull an H.
yeah,
out.
okay. I think this is G. And this
I
is
think
A.
those. I didn't even see those. Okay. Okay. Yeah. Okay. Yeah. Well, I mean, let's see. I mean, obviously you can work this out for real. So we're modding out by 180-degree rotations, and then also modding out by shifting to the right. Yeah.
Yes.
Just making
That's
sure
right.
that you've done that. Yeah. So yeah, it does look like you really did that. Okay.
That's right. And so we have, let's see, we have green ones and blue ones and red ones. And we have, let's see, so the green ones, okay. So what happened? I did it in some different order than usual. So this is A and B are down here. A and B are red, is that right? And then the blues are what? E and F and G and H. I usually do this in a different order with A's at the A and B at the top, and is this the way it goes? I think that's right. But right, so these are the bad fibers, the ones that have, you know, some point has multiplicity. So we'd like to figure out what these bad multiplicities, what these multiplicities are. And the multiplicity should add up to 6, right? So right, I mean, in principle, this is something we can figure out. But let's see. So is like let's see. So right, the multiplicity is like how busy these things are. If it has more edges coming out of it, it's higher multiplicity. And if you know what you're doing, you just count the edges coming out, and that'll tell you the multiplicity. Let's see if we can get some of the multiplicities here. Let's look at A and try to figure out what the multiplicity of, right, we're trying to get a multiplicity of A and a multiplicity of B. And they should add up to 6.
Stop saying what you should do.
What? That's too much cheating for you? Yeah.
Yeah. I can. Yeah.
Well, let's try. Let's cheat on the reds, and let's, you know, do it systematically on the blues and greens or something like that. So it looks to me like, you know, B has an edge to H and an edge to G, and maybe that's it. Maybe that. Let's see. B has. I'm thinking
Mod
that
it out by 180-degree rotation, so you just say there's one edge to H, right? That's
I think. I hope, yeah, I hope that. It looks to me, I'm going to try to claim that
that's
B
multiplicity
has,
of one.
no, I'm going to say multiplicity 2 because of the H and the G.
Oh, sorry, they're both blue. Yeah, sorry. Yep.
Now,
Wait.
I'm hoping it's going to work out that A,
So that has edges to E, F.
okay, yeah, there is a trick here. Let me put in a trick here. So you have to remember that, right? It's actually the half lozenges that are the Coxeter simplexes or something like that. So what does it go? It goes like this. Sorry, that was supposed to be different color, like see better. Orange. I could see better, maybe see worse or something like that. I think it looks like this. Is orange halfway visible?
Yeah. Orange is always much less charismatic in web applications than you think of when you think of orange. This is like a sickly.
Okay.
No.
So let's
know
try
why
to
we
count.
need
Let's try counting the edges now. And
that doesn't help me at all. But I think there's, I think there are 3 coming out of A. What do you think?
I'm guessing that there are going to be 6 coming out of A. Let's see. So let's see. What does A touch? A touches
Oh God.
C, E, F, H, and D. Oh, but it might touch one of them more than once. I think that's part of what's but it.
That's what was confusing me, I guess. So A seems to have 2 different edges to F, for example.
I'm hoping that's the only one that has 2 different edges too, because it touches 5 of them, right? C, E, F, H, D. And you're saying it touches F twice.
But why are you counting edges both to the blues and to the greens? I thought when you're like counting the multiplicity of a pole.
Well, I was hoping it would make sense this way.
I mean, with your B, you're only counting. Oh yeah, you're only counting edges to blues when you're doing B, right?
Yeah, I mean, right there are different conventions that you can use, and the calculation of the multiplicity works out differently in different conventions, and I'm probably blurring them all together. What?
Yeah, yeah, you seem to be changing them midstream to get what you want. So we discussed this once before.
Yeah, I'm hoping it's gonna, like I said, it has to add up to 6. So if it's gonna work out the way I said, it's gonna be 4 and 2. Let's see if we can convince ourselves that it really is 4 and 2. So let's see. So A, B. Yeah, it looks okay. It looks to me like A is busier than B is, because B is right at the origin, so it gets the full brunt of modding out by 180 degrees.
Right.
And
yeah, okay. So I think it's claimed that A has 2 different edges to F, 1 to H, and 1 to E. Yeah, okay. So anyway.
I was afraid that it had 2 to D or something. So okay.
But D is not a blue. Don't count the red. Don't count the green.
Okay, you're claiming. Okay, it sounds like you're claiming that I can just ignore the oranges. Is the oranges going away? No, I can't get rid of the rest of the orange. Okay, but
anyway.
But you think it works out like this? 4.
Yeah, I am.
And 2. Okay, and what about the G's, the greens?
C and D. Which one is busier? Again, I'm pretty sure it's gonna be 4 versus 2, but I'm not sure which one is the 4 and which one is the 2. There's
Sorry, what are you trying to do? C and D now?
C and D, yes, the green ones. How busy are they? You know, what's their multiplicity? Should add up to 6. And you should be able to get it by counting the edges and thinking correctly, but I'm not very good at thinking correctly at the moment. Well, all right.
So CS seems to have.
Yeah.
2 different edges to a blue. Namely, one edge to F and one edge to E. I don't think you need to go.
So what do you
need to go out
predicting?
of? I'm predicting 2
For C or for D?
for C.
For C. Okay, and then I'm predicting 4 for D because you said 2 for C. And is there any way to figure out the EF and GH? Should add up to 6? I think
2 of them are going to be 1 and 2 of them are going to be 2, but I'm not quite sure which are. Should we try to figure it out right now, or will you just accept for the moment that I think it's going to end up with 2 of them are going to be 2 and 2 of them are going to be 1? Is there any way to easily count? What?
I don't know if I like this game. It sounds like you know what answer you want to get, and then like, how you get it doesn't matter so much. This is
No, but I mean, it's clear there is a correct way to do it. You know,
oh, I see.
and at this point, we basically need the answers to talk about what we're going to do with the K-raters.
See, okay, so the red thing is going to give us a Young diagram that looks like 4 and 2. And the green thing is also going to give us a Young diagram that looks like 4 and 2. But the blue thing is going to give us a Young diagram that looks like 2 and 2 and 1 and 1, which by some sort of coincidence is the same Young diagram except flipped on its side or something like that. But see, this tells us what these K-raters look like. So the green K-rater is going to look like what? The green K-rater is going to look like.
Can you just remind me what these Young diagrams mean? I almost remember, but I don't quite.
It gives the multiplicity pattern of the K-rater.
Oh, okay. So it's just what we worked out. Okay. Yep.
Yes. Yes. So we're saying that the green K-rater should look like something like. Let me go up here. Let me look at it again. It was the green had C and C. What C was what? C was the 4. No, C was the 2, and D was the 4. So it would be X minus C to the squared, and X minus D to the 4th.
So that's what the green K-rater looks like.
And what does the blue K-rater look like? It looks like, well, so now I really am cheating because what do we have? We had
E, F, and G and H. And I claimed that 2 of them are 2 and 2 of them are multiplicity 2 and 2 of them are multiplicity 1. But we didn't figure out which is which. Let's just pretend that, it's like X minus E squared. And I'm sure this is wrong, but let's just pretend that it's like that. And X minus F squared and X minus G to the 1 and X minus H to the 1. So that's what the blue K-rater looks like.
Mm-hmm.
And the red K-rater looks like, X minus A to some power and X minus B to some power. And what did we have? We had A being the 4th power and X minus B being the 2nd power. So by the way, right, when we were talking about the roots, no, when we were talking about the we talked about crossing the discriminant, right? But that idea of crossing the discriminant, where this path in polynomial space where it crosses the discriminant, that's sort of based on thinking in terms of the coefficients of the polynomials. But if you're thinking in terms of the roots of the polynomials, and here we are sort of thinking in terms of the roots of the polynomials, because we're giving individual names to some of them at least. Because we're thinking in terms of roots instead of coefficients, you could actually think of these, right? Right, there's like a secret cryptomorphism between discriminant varieties in the coefficient picture and simply diagonal varieties in the associated to each Young diagram, there's kind of a lobe or something of the general discriminant. That's the D discriminant. If D is a Young diagram, then there's the D discriminant, which is like this lobe or something of the general discriminant where the multiplicity pattern is exactly like D. But if you're thinking in terms of the roots picture, then it's, the D diagonal rather than the D discriminant. So I think the way we're going to do it here, it's like we're probably thinking more in terms of thinking about the diagonal subvarieties, which are a little bit more intuitive, right? It's very easy to write down the equations for the diagonal subvarieties. Whereas if you want to write down the equations for the discriminant subvarieties, then, you have to kind of think. And the diagonal subvarieties look very straight and straight-sided.
Yeah.
Discriminant varieties are these weird folded up curved things. But yeah, so we're just trying to contrive a rational function which construed as a path in polynomial space is just like a straight line between three of these things. So you know what I'm saying? We're trying to say we're trying to find a straight line in polynomial space that that goes through 3 points like this. So we're trying to write down a system of equations that says we want these values A, B, C, D, E, F, G, and H, such that this will give us this straight line in polynomial space. So we want the coefficients of this green k-iterator. What am I trying to say? Well, we want these three polynomials to be collinear in polynomial space. So we just have to work out the algebra of things being collinear, which presumably we're supposed to remember from high school or something like that. How to check whether 3 points lie on the same line or something like that. And so and more specifically, this is
you're trying to figure out what equations on all these A through H are exactly necessary and sufficient to make that
yes
happen. Right.
That's right.
Do you even remember or care which one of these guys is P, Q, and R? Or collinearity doesn't really depend on who's.
That's right. Maybe at some point it's convenient to have a convention about that, but at this point it doesn't even seem to matter. We're just we're just trying to get P. Well, let me draw 3 points on a line or something like that. That's supposed to be on a line.
Wow, okay.
P, Q, R or something like that.
Uh-huh.
That's supposed to be a straight line.
Yep.
So if we have, and let's say this is, in Cartesian coordinate space with some coordinates or something like that. So if we have, some coordinate, like let's say, for example, I mean, yeah, you're right. Our actual things are going to be in a 6-dimensional space, a 6-dimensional space of 6th-degree monic polynomials.
Mm-hmm.
But let's just think about some 2 coordinates for the moment. I'll just call them X and Y for the moment.
Mhm.
Maybe that conflicts with it, but we're just doing a side calculation here. So I'm just saying that, the way I would think of it would be that, don't tell me, that Q, so the X coordinate, no, maybe I should do it the other way around. I don't know, should I call it Q sub X or X sub Q? The X coordinate of Q.
People would call that Q sub X, the X. Q equals QX comma QY in this baby version. Yeah.
Okay. Okay. So I want to say QX minus P. No, what am I trying to say?
You're trying to say the difference.
Yeah, RX minus Q of X over Q of X minus P of X
Is the same with Y.
is the same with Y, right?
Yeah.
So you cross multiply and you get something with 8 terms. Yeah, let me just write it down. So what did you say? RY
Yeah.
minus QY. What is it? QY minus P. Right. So you cross multiply, whatever you call it, and you get 8 terms. But 2 out of those 8 terms cancel out. Right. What am I trying to say? The Q's.
Really?
Yeah, there's a QX times QY
Oh yeah, right. On both sides.
in both cases.
Yep.
So that gets you down from 8 terms to 6 terms.
Mm-hmm.
And if you think about it, those 6 terms correspond to the 6 permutations of P, Q, and R.
Mm-hmm.
And this is really just a kind of a determinant of, what are we trying to say? We've got like 1, 1, 1, and P sub X and Q sub X and R sub X and P sub Y and Q sub Y and R sub Y or something like that.
Mm-hmm.
So we're just kind of saying that the determinant, and somehow the 1s are there because we're dealing with affine linearity instead of linear linearity or something like that.
Okay, that's cool. Yep.
I mean, right, presumably certain, I was gonna say certain people are supposed to know about this. I mean, some people do know actually about it. We're probably supposed to know about it, but I'm just faking this, pretending that I know how to do this. So, we just go ahead and do that.
So that was for
2 coordinates X and Y, yeah.
So now you want to do it for 6?
Yeah, so you have to have all these, you have a bunch of 3x3 minors. 3x3 minor determinants.
I don't want to do this, so okay.
What did you're commenting on the fact that we don't want to actually do the.
Well, maybe you
We don't want to go through the whole thing, but we're trying to convince ourselves that it works out very easily.
You mean you're going to actually try to get the answer, but you're
Today, no, not right now.
Okay.
I'm right now. I'm just sketching out how easy it is to do this. I mean, right?
Okay. Well, I mean, easy in the sense of you don't need to know much more than high school math, but hard in the sense that you're got loads of equations.
Well, yeah, but it's not that many, and the equations and the constraints kind of balance out. So
how many equations are you supposed to get? So for the little baby version, you got just 1 equation, right?
Right.
And so
So that was with 2 coordinates, but we have 6 coordinates, so we should have 5 equations, and we had 8 variables.
So you're saying to tell if 3 points are on a line in 6 dimensions.
If I didn't screw up, then yes.
You need 5.
Is that true?
I'm trying
hoping
to
that's
think.
true.
5 equations. So I could, the first 2 points could be anything, and then the third guy has to lie on that line, which is a one-dimensional subspace of a 6-dimensional space. So yeah, it needs 5 equations. Yeah.
I think that's right. And we started with, 8 variables, A, B, C, D, E, F, G, H.
Okay.
So, that's a deficit of approximately 3.
Mhm.
But
And
that 3 is, that 3, that sounds like the 3 of the triple transitivity. So I have good reason to think that this, balances out so that we get something that's sort of like a 0-dimensional variety when you take the triple transitivity into account. The 0-dimensional space of orbits under the Möbius transformation group or something like that.
And you're trying to get, I'm getting really confused. So when you're done, you get a discrete set of orbits, and they are supposed to be, what are they supposed to be?
Those are candidates for the Belyi functions for these diagrams. So we've narrowed it down to like a finite number of possibilities. This is, this is 0-dimensional algebraic variety.
And all this was for some particular Gaussian design.
That's right. That's
So
right.
what would it mean if it had more than one Belyi function?
Say it again.
What would it mean for it to have more than one Belyi function?
For what to have more than one Belyi function? The design can't have more than. I mean.
Well, that's why I'm worried. Yeah.
Yeah. No. The designs have.
I mean, all this stuff in that box there, that was for one design, right? When you were doing.
Yes.
We alluded to like 2 designs that were interested.
Right. But we created this system of equations not knowing full combinatorial information about the design. We took only a very limited amount of combinatorial information about the design, and we were able to create this system of equations from that. And basically, it's just kind of the combinatorial data that we used was this thing I call the vertex censuses. You just
okay, right.
For each vertex, you keep track of what the multiplicity is, the multiplicity of edges or something like that. And different designs can share that same data. And so different design, the ones that share the same data have a chance of being in the same Grothendieck-Teichmüller orbit. But
do they need do two in the same Grothendieck-Teichmüller orbit need to have that same bunch of young diagrams?
I think so, because they have to be, they have to be the same. They have to be the same.
Oh, could you say it's because like the Galois groups?
Yeah, they have to be equivalent under the action of the absolute Galois group.
Yeah, and 0 and 1 and infinity don't get budged, so they must behave the same at those points. That is the.
Yeah. So.
Okay.
Right. So, if they're in the same Grothendieck-Teichmüller orbit, that they're the same under the action. I mean, maybe I'm assuming some big conjecture here about that the Grothendieck-Teichmüller group is the same as the Galois group or something like that. Yeah, same as the absolute Galois group or something like that. But it's reasonable, under the reasonable assumptions like that, that the what am I trying to say? That 2 things in the same Grothendieck-Teichmüller orbit, since they're really the same thing up to Galois automorphisms of the algebraic numbers, they have to share any property that you can express in terms of rational algebra.
Yeah.
And we managed to express this idea of the vertex censuses in terms of the rational algebra.
Right.
So
yeah. But you have no special reason to think that everybody with the same vertex sentences are in the same Grothendieck-Teichmuller orbit. That would be like some other.
For the case of general designs rather than Gaussian designs, we know that that's false. We could probably easily come up with examples, but there are good textbook examples of that kind of thing. I think, yeah, I'm pretty sure there are good textbook examples of designs that share the same vertex census, share all, the same census of all the vertexes of all colors, but that are not in the same Grothendieck-Teichmuller orbit. So yeah, so this, this little zero-dimensional algebraic variety that we're getting breaks up into components, and it breaks up into different number of components depending on whether you're doing the breaking up over the rational numbers or over the algebraic closure of the rational numbers. And so if you're doing the breaking up over the rational numbers, then those components are the Grothendieck-Teichmuller orbits, I think, more or less by definition. But somehow we want to single out the one that we really want, and we have to try to learn to express more geometric information than just the vertex censuses. We want to express it in purely rational algebra, I guess. But then you also want to think about, sometimes you want to think about, how we can break this up, how we can factor this system, break it up, decompose it over the algebraic closure of the rationals. And in that case, it breaks up in a finer way, and that actually gives multiple designs that are in this that are combinatorially different, but that are in some ways they are combinatorially different, even though they share very coarse things like the vertex censuses. And so they're the same Grothendieck-Teichmuller orbit, but they're combinatorially different. So that the action of the Galois group here is acting in this funny shape-shifting way, that it actually changes the shape of geometric objects when you and I halfway understand this idea of how the Galois group succeeds in shape-shifting things, but I'm trying to understand it better. So that's a big part of what we're trying to do here. So yeah, but right. So I mean, this system of equations that we wrote down is not the end of the story, because we need more constraints that will get us down to just a single Grothendieck-Teichmuller orbit. But it's not the end of the story, but it's a good start. And it's and it's also a good start in trying to settle these conjectures about how the Jugendtraum relates to the designs. And that's this with this specifically of the Gaussian nature of these designs, that it relates to the Gaussian integers. And okay, so I'm hoping what we just described is not that bad, and you can see what its intended purpose is, and hopefully you can see that working it out is not that bad. It just turns out to be this high school algebra about collinearity. But now, right, so that's so we have conjectures, a conjecture, or perhaps multiple conjectures, or slight variations, multiple variations on a conjecture here, and we want to check them. So we really want to have another calculation that we can check against this calculation. So we haven't actually carried out this calculation yet, but I am claiming that it's really this is a pretty definite calculation. We just need to work it out. I also want to get computers and things to work it out for me and stuff like that. But it's very precisely specified. Working out this zero-dimensional algebraic variety. And when I say very precisely specified, that's a little bit of an exaggeration, but it's appropriately specified. It's specified just enough that you can actually do the concrete calculations, I think. So like I say, I want to have another calculation that I can check this against. And so I have another bunch of calculations here that I haven't worked out in detail at all yet. But it should be, in principle, fun to work out, about as much fun as this other one. So let's start thinking about this other way of trying to understand these Gaussian designs.
Okay.
And this is basically, so this second calculation, or bunch of calculations, is basically just trying to understand the same designs, the same Gaussian designs, but trying to use relatively humble techniques involving, old-fashioned techniques for calculating Gaussian addition on the Gaussian elliptic curve. So, yeah, let me right. Right. We still have a bunch of time left. I'm not taking so long to say things, not quite so long to say things as I usually do. So I've actually got a little time left here. So we actually can do 2 parts of the project here instead of just 1 part. So what am I trying to say here? I'm trying to pretend to draw like the Gaussian elliptic curve or something like that. So yeah, I mean, one way to think about it is it's like y squared equals x cubed minus x, which is equal to what? That's equal to x minus 1 times x minus 0 times x plus 1. Or x plus 1 is also x minus 1 or something like that. Of course, there may be other variants on this. We might find preferable to use some other coordinate change or something like that. Maybe, I mean, in this case, one of the 4 branch points is at infinity, but sometimes it's more convenient to put all 4 branch points on the unit circle or something like that. The 4 quadrants, 4 points of the unit circle or something like that. So, okay, I'm trying to orient myself to the mental pictures I'm supposed to be thinking about here. So what am I trying to say? There's this cubic polynomial x cubed minus x, and I'm x cubed minus x. I'm imagining that it looks something like, that's supposed to be -1, 0, and 1, and it goes something like, something like that. Agree? Very, very, very roughly. Very, very qualitative.
Yep, it's fine. Yep.
But then you take its square root, and the only parts that are visible are the parts that are above water. So there's like a little thing there. I'm not scaling this very carefully, but right, it's something like, what am I trying to say? It's something like that or something like that.
Yep.
So this is the real part of this way of thinking about the Gaussian elliptic curve. There's also the imaginary or complex parts or whatever. But so what? This like rules about when you have there's a funny coincidence going on here, right? In the first half of the discussion, we ended up dealing with collinearity in polynomial space. But in this second half of the discussion, we're talking about, the usual collinearity thing about Gaussian addition. That, how does that work? That, these 3 points where these 3 collinear points on the Gaussian elliptic curve add up to
0 in Gaussian addition.
Yep.
And and Gaussian negative is just up down thing, right? So if you actually want to add these two things together, the two on the left hand side, it would be the negative of this thing. So that would be like down here or something like that, right? So this would be A and B, and this would be A plus B or something like that.
Yep. Yeah, this is the stuff I learned when I was first learning about elliptic curves that I hated, but now I can take it probably. Yeah.
Right. Depending on your viewpoint, it can seem very oppressive, or it can actually seem like fun. Yeah, so I have reasons why it's fun for me at this point, or potentially fun. But so we want to do things like we want to right. So an example of right, there's all sorts of fun little things going on here, but right. So I mean, if we go back to our designs up here, again, they're very mod 3-ish. Our designs. So right, if what am I trying to say? That right, this has a lot to do with 3 torsion. The 3 torsion on the Gaussian elliptic curve. Right, so on the Gaussian elliptic curve, there are these 9 3 torsion points. They're kind of the kernel of this wrapping, this 9-fold wrapping of the, multiplication by 3. Yeah, multiplying Gaussian integers by the Gaussian integer 3 kind of gives us this 9-fold wrapping of the Gaussian elliptic curve by itself. And that Gaussian elliptic curve, it's an abelian, and so and this is this wrapping is a homomorphism, and you can talk about the kernel of that homomorphism, and that's the 3 torsion. And it's these, you can think of it as these red points. If you think of this as the Gaussian elliptic curve, this torus that's wrapped up, then the red points are these, you can think of that as the 3 torsion points here. And so what am I trying to say? That, yeah, I'm taking a long, now I am taking a long time to say some very famous, obvious fact that what, so we're looking at, we're interested in the 3 torsion points, which are the points where this is equal to 0.
But you should
with
write
respect to
it
Gaussian addition now. What?
Right. But it sounds like you want to write it as A plus A equals negative A.
Actually,
Let's see.
I may have thought that's what I wanted, but now that I look at it, it actually seems more fun to just think of it as A plus A equals 0. Because, right, this does translate into a pleasant geometric fact. This is saying that the 3 torsion points are the so-called inflection points on the curve. And I forget exactly what inflection points means, but I think it really is, some naive concept of inflection point here or something like that, where it switches from being convex one way to being convex the other way or something like that. So, there should be 9 3 torsion points, but it makes sense that only 3 of them would be real in this picture.
So why are they the inflection points?
Because, you've got A, B, and C here. And, A plus B plus C equals
right.
0.
Okay, yeah, right.
So
Okay.
if A is equal to B and B is equal to C, that's called an inflection point. So, there's this
line here, sorry. What am I trying to say? There's a line right there. And it intersects, there's a straight line there that goes through this blue point. And it intersects this Gaussian elliptic curve in 3 points, or it intersects it with multiplicity 3. Right. It intersects it in 3 identical points. That's what an inflection point is. Again, I'm being sloppy here, but this must be true, right?
That really, sorry, let me just think about that a minute.
Okay.
Okay, yeah. Okay. So a normal tangent, a generic tangent point to a smooth curve is intersecting it in 2 identical points. Yeah, right. Okay.
That's right. Yeah. It's something like that. Yeah. The derivative is 0, but here the second derivative is 0. So
okay. Yep. So
right. It's a higher critical point. So yes.
So you drew 2 of them there. The 2 blue guys. Is there a third guy? The third inflection point?
The one at infinity.
Oh, okay.
Oh, yeah, the one at infinity. And then there are these imaginary ones or complex ones that we can't really see.
Yeah.
But they're there. And they're called, they still are inflection points. They're just complex inflection points. And there's this ideal inflection point at infinity.
Yeah.
And
okay,
yeah.
that's yeah, there's the kind of stuff I used to hate, but yeah, it's okay. It's fine. It's just I just hated it before or right around when I realized that elliptic curves are actually just parallelograms of their edges wrapped up, which seems like tons easier to think about. But anyway, now
right.
Okay.
But
yeah.
right there,
There are people who try to introduce elliptic curves this way, and I think it should be put off. But yeah, it's okay.
Yeah, there are really big arguments about how it should be approached. But
anyway,
yeah, you probably don't really understand elliptic curves unless you've had the experience of finding this approach oppressive. But you also don't understand them
That's why
unless you have had the experience of finding it fun. What?
I see. So that's why they start out with this approach. So like, it's to
Yeah,
make you get really excited about the next.
That's part. Yeah, I'm not sure what's the.
Okay, so what is
I mean,
this?
no matter which way you zigzag, you're still gonna have some parts that seem oppressed, or it's very tricky trying to figure out the path that takes you through it without feeling annoyed at some point.
Yeah.
And I'm not claiming to have that path here. But so yeah, so we can write, we can write using these ideas, we can write down some system of equations. Again, I haven't worked this out in very much detail yet, but we can work out some system of equations that kind of says, you know, we should be able to write down equations about A and B and C and D and E and F and G and H in terms of this way of thinking, in terms of thinking about Gaussian addition. And again, it's a funny coincidence that both of these calculations involve thinking about collinearity, but in very different spaces, as far as I can tell. It seems to me like it's just a coincidence, but that would be fun if it turned out to be not a coincidence. That, you know, the one calculation involves collinearity in the space of 6-degree polynomials. The other one involves collinearity in the, you know, the XY plane where the Gaussian elliptic curve lives. That sounds to me like a coincidence, but it'd be fun if it wasn't a coincidence.
Yeah.
Right. So that first calculation, you know, we practically did everything except actually work it out. But for the second calculation, I'm being very much more vague about it, because it involves not just this 9-fold cover, but also these 3-fold covers. You know, and you know, you can think in terms of unwrapping, or you can think in terms of wrapping. So if you're thinking, what am I trying to say? If you think in terms of wrapping, then it kind of involves 3 torsion points. If you think of it in terms of unwrapping, then it's a little bit more elegant and you're really thinking about Gaussian integers and stuff. But anyway, right? So, right, do you see what I'm saying? There's a,
I don't quite get what the goal is of this.
the goal is to prove that we're getting, the goal is to prove that that the system of equations that we should get when we work out this Gaussian addition stuff should imply the system of equations that we got from the design thinking, from the K-rater way of thinking. That's the goal. We're trying to show that we're on the right track here, that the Jugendtraum is really going to connect up to the.
Yeah, that's too grandiose. But so you're trying to.
Yeah. It's actually not too grandiose. Go ahead. Yeah.
Trying to get a specific.
Exactly as grandiose as it should be. Go ahead.
Well,
Yeah.
for itself, but no, but for what I'm. Okay, so the calculation isn't to connect the Jugendtraum and blah blah blah. The calculation is to try to get a formula for the covering map from this elliptic curve to the projective line. A formula for it?
Yeah, no, it's right. What we're really trying to get a formula for, or solutions. We're trying to get. We have systems of equations, and we're going to get the solutions to those systems of equations, and those solutions, the coordinates of those solutions, are the locations of these vertexes on this genus zero design. So, we're going to have one system of equations that's based on Gaussian addition, and it's going to tell us where these vertexes should be by thinking in terms of Gaussian addition. Where on the Riemann sphere should these red vertexes lie, these green vertexes lie, the blue vertexes lie, and it's all based on the sort of Gaussian addition relationships between in the arrangement of the green and red and blue dots here.
I'm completely confused. I thought when you're thinking of a
I'm being sloppy, but I was hoping
covering the Riemann sphere, all the red points are getting mapped to 0 and all the blah blah.
Well, that's why I said it depends on whether you take the wrapping viewpoint or the unwrapping viewpoint. So
you want to think of their positions in I don't know what, in the complex.
Yeah, right there, there's a covering projection here. There's a wrapping here, or an unwrapping here. So it's the unwrapping has the upstairs and the downstairs. The upstairs is the unwrapped. No, the upstairs is the unwrapped thing, and the downstairs is the wrapped up thing. So you've got, downstairs you just have a single point, but upstairs you have a whole fiber. So like for these ninefold things, you have 9 things, but we have all these sixfold things. How do we get both a ninefold and a sixfold? I don't know. I'm not going to worry about that right now. But it does work out somehow that there are relevant ninefold things and relevant sixfold things.
So the downstairs thing is the Riemann sphere, and the upstairs is an elliptic curve. Is that what you're talking about?
There's a whole bunch of things here. So there's one of the unwrappings that we're interested in here has downstairs is an elliptic curve, and upstairs is another elliptic curve.
Mm-hmm.
And and it's a ninefold wrapping or something like that.
Okay. But which one? What one were you trying to calculate? Something about using the formula for addition in elliptic curves. Sorry, I'm confused about what it is.
Yeah, finding for example, finding the locations of the red points. So like I say, the red points are just the three. From one viewpoint, you can think of them as the 3 torsion points. on the Gaussian elliptic curve. I say the red points on this design, the red points on this design that has 9 red points.
Okay, well, yeah. So I mean, from one point of view, the locations of the red points are exactly what you drew right there, and that they are those red dots. So there's nothing to calculate there. But now you're gonna, so you're, for some reason you say you want to reinterpret that elliptic curve in terms of this drawing that you drew, that's like the drawing I always used to hate, and think of them that way. So why do you, what does it help to draw them, to find out their locations from that point of view?
So we compare it to what the other calculation is telling us. The other calculation is predicting what are the locations of the green and blue and red points. So yeah, I mean, you know, what does the Riemann sphere look like? It looks something like this.
Maybe.
But really, it looks like a tetrahedron or something like that. And that tetrahedron, right? This is like got these acute triangles, and it's really just like, you know, these acute triangles that are arranged in this. Right? There's the whole thing about the acute triangles and how they wrap around.
Yep.
Right. Right. When you have the genus 1 flat thing, there's 6 triangles to a corner. But when you have the genus 0 curved thing, there's just 3 triangles to a corner. Just a tetrahedron, 3 triangles to a corner. In the double cover, you have 6 triangles to a corner. And it all fits together very nicely. The genus 1 thing covers the genus 0 thing with these 4 points or something. And so on the Riemann sphere, you know, we have this somewhere we have these designs that have like just 2 red points somewhere and 2 green points and 4 blue points. I'm not sure exactly where they look like. And, you know, they have these edges between them. I'm not, you know, I'm just pretending to draw it in there, something like that. Something like that. And, you know, the K-arator Young diagram calculations should be telling us where these points, you know, what are the numerical coordinates of these points on the Riemann sphere. Once we perhaps, you know, normalize it by naming a particular red and calling it infinity, naming a particular blue and calling it 0, and naming a particular green and calling it 1 or something like that. You know, when you normalize it enough, then you get actual numerical coordinates for all of the vertexes of everything over here. And on the other hand, if we do it right, and that's where I'm being really sloppy, is, you know, if we work out this Gaussian addition stuff, then that should also tell us, right? I mean, so one of the things we're saying, right, is that we've got this picture of the Gaussian elliptic curve. And here we're saying that to get the genus 0 thing, you just ignore the y coordinate and only look at the x coordinate. Right? So you'll end up with these things that just lie on the Riemann sphere. And so, do you see what I'm saying? There's 2 calculations or 2 groups of calculations that can be compared here if we work things out correctly. And, you know,
yeah, I guess I get it.
And if the 2 calculations agree in the correct sense, then that is telling us that we're on the right track in connecting. That we're on the right track in placing the Jugendtraum inside the context of Grothendieck's design theory, or Drinfeld's Grothendieck-Teichmuller theory. And it's Much later than expected, but it's also very close to a natural stopping point because we're like totally running out of time here.
Yeah.
Boy, there certainly were other things I really wanted to tell you today, but we did reach a natural stopping point. So is there anything we have in our last 30 seconds? Is there anything we should try to say?
No, we gotta quit.
Okay, I'll see you.